All right, hello sixth grade. Here are your review notes for the folds, faults, and earthquake notes. So we start with thinking about the folding and faulting of the earth. Now the rocks in the crust of the earth can either fold or they can fault or break, as we'll see. And there are three factors that can determine whether the rocks will fold or fault. The first is pressure. If rocks feel a lot of pressure, they'll likely fault and break. If they feel a little bit of pressure, they'll likely fold. That's what we have right there. The second factor is temperature. If temperatures are warmer, it makes the rocks a little more flexible. So warmer rocks, especially rocks that are maybe deep and closer to the mantle of the earth, rocks that are warmer will likely fold. Think of kind of like gooey brownies that could fold a little bit. Rocks that are cooler will likely fault. Once those brownies get cooler, they can crack and fall apart a little bit. So think of like warm, moist brownies that can bend, or cold, old brownies that can break apart. And the third factor of whether a rock will fold or fault is the type of rock, depending on what it is. Some rocks, just because of the way they're made up and the minerals that are in them, are brittle. And if something's brittle, it means it breaks easily. So granite is an example of a type of rock that is just more brittle. It'll tend to break more easier than fold. Other rocks are a little more flexible, and they'll likely fold. So like sandstone is a type of rock that's more flexible. So the three things that determine whether rocks will fold or fault, is the pressure, it's the temperature, and the type of rock that's feeling the temperature and the pressure. Okay. Now, of those two things, first we'll look at folding. And there are three main types of folding I want you to think about. The first is an anticline, and that's when you have layers of rocks that feel some compression, and they squish together such that they create sort of an arch here. That's an anticline. You can remember that by little a. You can think of the a in there in the middle. You can also have a syncline. That's where rocks are pushed together and they sort of sink down. Think of it like a sink. And the third kind is the anticline-syncline combination. Most of the time, this is really what you'll see, is that there's a combination. It's kind of like if you had a rug, and all of a sudden you squish that rug, the rug gets all of these hills and valleys up and down, up and down. That can happen to rocks. There's also a monocline. We won't really worry too much about a monocline, but basically where there's a little bit of pressure, only one side dips down a little bit. But the three I want you to think about are the anticline, syncline, and the fact that they can be combined together. And, it's the same slide twice. One thing to think about is, what do these anticlines and synclines look like on the ground? And a lot of times they've been eroded away such that you see only exposed rocks. They started flat, they got pushed together, and they created anticline and synclines, but then the rocks were washed away. So as geologist Jane walks across here, she's on different types of rocks depending on how they were pushed together. And you can see that in these drawings. Here's an example of an anticline. And we told the story of how Jane walked across here and took samples of the different rock types as she went across and could figure out that there was an anticline based on the fact that they were the rocks were tilted away, sloping away from the center. We also mentioned that with anticline, sometimes oil and gas can get stuck under there in the anticline. This is really helpful for geologists who want to find oil and gas as a means to make gasoline and other types of fuels that we use. So it really is important that geologists think about these things and look for these features in the earth so they can find resources that people can use. You could also, there's a monocline. This slide's not so great. Just skip this one. And here's a syncline, same idea. Jane walks across there, she goes across and finds the different types of rocks and can figure out what's underneath her based off the evidence of the samples that she finds on the top. Okay, now to faults. There are three types of faults caused by three types of forces that are found in three types of plate boundaries. So the first type of fault is a strike-slip fault, and that is formed by a shearing force, a scissor type of force. And when you have a strike-slip force, the earth is squished sideways relative to each other, and it slides in two directions. So if we had a road, if we're looking down on a road and there was a fault line, and it felt, a fault line, by the way, is the line in which the earth actually moves across. So it's kind of like where the rubbing and the moving actually occurs. If this area felt a strike-slip fault, felt a shearing force, this side of the road would go this direction, and this side would go this direction, and it would slide past each other. These are caused mostly at transform plate boundaries because that's what the plates are doing. They're moving side to side relative to each other. Another kind of fault is called a normal fault. So now we have a side view. And with a normal fault, if the rocks are being pulled apart, we call it pulling force or a tension force. It causes one rock to go higher than the other and creates, like I said, a normal fault. So there we see a normal fault. Here's Jane and the tree. Then there's an earthquake and the faults move. And now Jane is higher than the earthquake. And the line between the two blocks creates an obtuse angle, which we'll talk about in a second. The normal faults, where they're being pulled apart, usually occur at a divergent plate boundary because the divergent forces create the tension forces, and that creates the normal faults. And the last kind is a reverse fault. A reverse fault is where there's a pushing, a compression force, a pushing force. And this time, where Jane and then there's the tree get pushed together, the reverse fault causes the other side to go up higher, and the angle in between them is an acute angle. And we can remember these by the word nora. If there's a normal angle, it's an obtuse. If there's a obtuse angle, it means it's a normal fault. So there's an obtuse angle, that's a normal fault. If it's a acute angle, it's a reverse fault. Acute angle, reverse fault. So nora can help you figure out and remember the difference between a normal fault and a reverse fault. This is just another picture of showing here there's lots of obtuse angles. They're slightly obtuse, which means that this whole area is being pulled apart, and it creates these features. They're called Horsten-Grabens, and these features can occur when pulling tension is pulling the crust apart. This is what happens before an entire plate might break apart at a divergent plate boundary. So this is a great page to review. It sums up all the different types of ideas for the 3 different types of faults. So the question is the direction of the movement, the type of boundary where that movement can occur, the faults that can occur, and the force that creates those faults. So if they're at a convergent plate boundary, the movement's coming together, it causes a compression that causes a reverse fault. At a divergent plate boundary, spreading apart, it creates a tension force that causes a normal fault. And lastly, you have a transform plate boundary. It's moving side to side. It causes a shearing type of force, and that creates a strike-slip fault. Review this page. Wink, wink, nudge, nudge. All right, here's the picture. We talked a little bit about how sometimes anticline and synclines can make unique features. It's neat to see that this is actually a syncline. It's sinking down, although the erosional aspect of it made the top of the hill the actual kind of top of the syncline there, which is a little odd, but it's kind of neat that sometimes it looks like that. Oh, we did the marshmallow challenge. That's a quick side note. Back to the earthquake notes. Okay, so an earthquake is when the rocks are being squished together and there's building up pressure, and all of a sudden they can't move anymore, and so they start to break and they move. And that break causes a release of energy. And this release of energy comes from a single point within the rocks, and it happens along a fault, and it releases energy outward from one single point. And we use the analogy of a duck and a frog in a pond. And if a pebble fell into the middle of the pond, the pebble would release energy as it hit in the water, and that energy would move through the water in the form of waves. And the duck that's near where the pebble went in would feel more of the energy because it was closer, and the frog that was farther away would feel less energy because the energy gets weaker and weaker as it spreads out away from where the energy originated, which in this case would be in the center of the pond. And this is true for earthquakes. Now, the types of waves that go out of an earthquake, there are 3 types. First is the primary wave. They move side to side, like a slinky squishing and spreading. They move the fastest, and so they also show up the first. They're called primary waves. The secondary waves move a little slower. They go up and down. An S wave, you can think of like that. And the last time is they both kind of come together and create surface waves. And these are the most damaging because they're on the surface. So first comes the primary waves, then the secondary waves, and then the surface waves. Here we see again where the earthquake occurs. It happens, the actual location where earthquake occurs is called the focus. And the focus is always deep underneath the earth. Now, we're not down there deep beneath the earth, but we're concerned about the closest point on the surface near that focus, and that is the epicenter. That epicenter is going to feel the earthquake's energy first, and everywhere around that will feel the energy second. So for us living on the surface of the earth, to us the energy seems like it's coming from the epicenter. And at least in terms of the surface it is, but truly it's coming from the focus underneath. The epicenter is the place directly above the focus of the earthquake. And so if you live near the epicenter of an earthquake, you're going to feel more of the energy, just like the duck was feeling more of the energy in the pond. If you live farther away from the epicenter, you'd feel less of the energy, just like the frog was feeling less farther away. Okay. Oh, some vocabulary. Seismologist. Someone who studies an earthquake. This, by the way, this vocabulary is a little different from your book, but I want you to stick with these. I think these are a little bit better to remember. A seismometer is a machine that measures the earthquake energy, and the seismometer, or the seismometer, makes a seismograph, which is sort of like a graph made by the seismometer that shows a seismologist how much energy an earthquake has. They can describe that energy in terms of magnitude, and the magnitude can be put together on the Richter scale. And the Richter scale is exponential. And in fact, this is actually incorrect. It's not 10 times better. It's actually, I think it's 32 times bigger from each step of the Richter scale. So 2 is 32 times bigger than a 1. A 3 is 32 times bigger than a 2, which means a 3 is 32 times bigger than a 1. Now, you don't need to remember that, but I do want you to remember that because it is exponential, earthquakes on the Richter scale that have a magnitude of way up in the 8, 9s, and 10s are really, really big. But that also means that earthquakes that have a 1 or a 2 are pretty small. You wouldn't be able to feel a 1 or a 2. Only a seismometer would be able to feel that. And to remember that, here's a little story I said about in college, how you have a building and you put the seismometer way down where the only thing that could shake it would be the shaking of an earthquake, and then that would send a signal to the seismograph that would tell how much it's shaking, and the seismologist would read that. And I told the story of how when I was at school, they were creating a new foundation for a new library, and they'd release explosives, and those explosives would cause mini earthquakes to rock through the rock underneath the school, and the seismometer in our geology building would be able to register the earthquake created by the explosive that they were using to make the new library. It was pretty awesome. Earthquake safety. I won't go through all of these, but we talked about those in class. Read those through. Definitely be prepared to know about earthquake safety, but you guys are becoming experts on that. Big question here. Can we predict where an earthquake occur? Yes, they occur near plate boundaries and where there's faults near plate boundaries. But can we predict when an earthquake can occur? No. It could happen, if you lived on a plate boundary, it could happen in the next minute. It could happen in the next year. It might take 10 years. You're not sure when it's going to occur, but you do know it's definitely going to occur near a plate boundary and much less likely to occur in the middle of a plate boundary. Still can, but not always. So then we talk about finding the epicenter, and we did that by, geologists can do that, seismologists can do that, by they figure out how far away the earthquake happened from certain cities, and they then create circles around their city that are the distance from which the earthquake occurred. We use this example where if San Francisco figured out the earthquake happened, say 25 miles away, they say, oh, this earthquake happened 25 miles away. It must have happened somewhere on this blue line because every place on this blue line is 25 miles away. Then the Stockton seismologist figured, well, actually for us it was 50 miles away. Well, this red line represents 50 miles away from Stockton, so it must have happened somewhere also on this red line. Well, there's only 2 places where the blue line and the red line are at the same place, here and here. And so they've narrowed it down to earthquake either happened right here or it happened right here. How they can determine which of those 2 locations is they talk to the third group. The third group of seismologists from Sacramento can say, well, this happened 150 miles away. And so they put in the green line. This is all the locations that are 150 miles away from the earthquake. And sure enough, it crosses over this location. So this must be the place. This is the place that's 150 miles from Sacramento and 50 miles from Stockton and 25 miles from San Francisco. For all those to be true, this is where the earthquake must have happened. And this is what you did skip this page for now. This is what you did in our earthquake activities. We saw that the P waves and the S waves split apart. And because the P waves go faster than the S waves, the time between the arrival of a P wave and the arrival of an S wave at a city is greater the farther the city is from the epicenter of the earthquake. And geologists then can use that difference of time using this chart, and you'll need to use this chart by knowing, well, if it took 4 minutes between the arrival of the P wave and the arrival of the S wave, then you move over here on the chart, drop it down right there. That's the distance the earthquake was from you. It looks like it was 2,000, 220, 240, 2,600 kilometers away, okay? If it was 2 minutes between the P wave and the S wave, the earthquake is approximately 1,000 kilometers away. Be sure you know how to use this. We practice this in class, and let me tell you, you might see this again. Be sure to be able to do that. And that's how we did our final activity of the classroom epicenter, is that we used, there we go, we used the the different times of the arrival of the P wave and the S wave to find the epicenter within the classroom.